Okay, students, looks like all systems are go and that the live stream is running. That is one of the most important things for the moment now. Let me check. Yeah, looks okay. Welcome to the continuation of Multibody Dynamics B. So it's like the second half, right? We're now already on a winning course. If we look at our homework average, for most of you that works, I guess. In the second half, we will have only 5 lectures. So in the first half we had 6. Well, the first was just organization stuff and panic and so on. So contents-wise we have 5 lectures. That's due to I have to go traveling and one of the weeks drops out because of some holiday or I don't know. Anyway, 5 lectures, 5 homework assignments, and the due date is always very clear. The due date is at the next lecture. Yeah. Office hours also shifted, of course, from Monday to Wednesday, same hours. Let's have a look at the schedule, the lecture schedule. So lectures. Yeah, so we're in the second half after the spring break. So this week we have a lecture, next week we have a lecture, then there's a break of 2 weeks, a session day and I'm traveling. And then we finish with 3 lectures. Well, we do not finish with 3 lectures, we finish of course with the digital exam. And the digital exam, don't be afraid. If you made your homework assignments by yourself or you copied from others but understood what you were doing, no problem. Then you will just pass the exam. And the grading is even such that if you get a higher score than all the other scores which you have had until now, then the highest score just wins. I mean, you get that high score. So last year we had a number of 10 out of 10s because they just did the 3 exam problems perfectly. And I will put an example of such an exam problem on the website. It will be Maple TA, sort of individual assignments, so you cannot pick next to your neighbor. I always was under the impression that everybody was using MATLAB. Until today I got an email like, hey, I'm using Python, and can I also run my Python scripts during the exam? I don't know, I'm going to find out. I think it's important, so I will put all my effort into it that will work. But I cannot guarantee now. I have to find out. Anything else? I'm so happy that all the technical stuff is working. It's always a pain, 15 minutes preparation. And 1 day in advance for me panicking. Questions from you at the moment. Is everything okay? Yeah.
This Maple TA platform, is it similar to MATLAB? What's it like?
No, it's a test environment. And you don't have to know that it's Maple TA. It can also be Coca-Cola. It doesn't matter. It's just a test environment. But on the computer you can run MATLAB, you can look at PDFs and at Microsoft documents, and that's it. You cannot communicate with the outer world or with your neighbor. Yeah. But I'll put an example which you then can run. Any other questions? No? Okay, let's kick off. So today, yeah, I have to go to this guy. 7th lecture, we're going to talk about numerical integration, but before we start we always do Kahoot. Yeah, let's do Kahoot. Okay. That was wrong, of course. Play, right? And I can make it a little bit bigger for everybody. Classic. And remember, somewhere in your ID should be your student ID. Somewhere in your name should be your student ID. Or your student ID also suffices by itself. And about the contents of the quiz, what can you expect? Well, it's mostly, of course, questions from the past period, so it's a bit randomized through the weeks. And of course, one question on the topic of today. Can you close the door a little bit? Otherwise I have all the background noise. Not completely, not locked, but yeah, oh yeah, oh, well, whatever. Okay, yeah, let's start. Five questions. Well, the first is, yeah, about the last homework assignment, right? Does anybody know, by the way, where this is? Nobody from Rotterdam in the audience? No? Okay. Actually too simple, huh? Oh. Tea time, yeah. Okay. Yeah, Jeannie or Johnny in the audience? Oh. Well, this is serious business. Take your time, you have 90 seconds. And talk to your neighbors. Convince your neighbor you have the right answer. You can use pencil and paper. But your neighbor need not be right, eh? Okay, so again, this is like what we say a learning moment, right? So apparently it's the first answer. Let's look at the problem again. For those who had it right, okay. For those who had it wrong, just make a note that you should check this. Yep. K in the audience? No. Well, this is a golden oldie. It's too quiet in the room. Please discuss. Yeah. No real problems there. Anouk? I saw a little hand go up. Yeah. Anouk, winner. You have 120 seconds, and please use pencil and paper and discuss with your neighbor. You've done the assignment, so you know what it's about. Oi, 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 oi. Okay, look at the correct answer. Yeah, and I will show the problem again. So now think where you made your error. Yeah. And of course, if you really want to resolve that, you can always look at the recording later and then check. Yeah. Okay, where were we? Is this the fourth question? I lost track. I think so, eh? Anonymous. Yeah, this is the last one. We're almost there. So you have enough time, think about an answer, discuss with your neighbor, say, I'm right, you're wrong, you're stupid, I'm smart, and vice versa. Yeah, okay. Yeah, there's a winner. Is the winner in the room? Hand up. No? Okay. Show the feedback. Please give feedback. I enjoy having feedback, either negative or positive. Every feedback is welcome. Save the result. Direct download. And save to the drive. A bit lower, 3.5. Well, whatever. Okay, we're done here. Let's go. Let me check if this is all running. Yep. Okay, contents for today. So the topic is numerical integration, and until now, so almost one whole quarter we have spent on solving accelerations, either from mass times acceleration is some generalized force, which was a function of the position, the coordinates, and time, or we had this very nice simple DAE approach with x double dot and lambdas and mass and C transpose and some right hand side forces, and here's some second order terms. It doesn't matter. Yeah. For whom? Okay, then I have a proposal. If I speak louder, then the whole audio gets fucked up. So there is a simple solution for that. And let's come forward, please. Yeah? We have enough seats in the front. Okay, so I will speak a little bit up, but I cannot do it too loud. So until now we solved for the accelerations, right? But what we actually want to know, we want to know the motion of the system. So in other words, we want to know what are the coordinates, Q, the generalized coordinates, or you could also say what are the CM coordinates as a function of time. That's what we are interested in. We're not interested in accelerations. Well, sometimes you are, and sometimes you want to know forces, but actually we want to know the motion. So how do we find the motion? Now, the problem is actually like this. Given at some moment in time, t0, I have coordinates q0 and I have speeds q dot. And then, of course, from the equation of motion, I can solve the accelerations at that time, q, t, q, and q dot. So I can solve them. So I actually also know what the accelerations are. And then the question is, at t1, which is a little bit further on, with a delta t further on, what are my positions, q1, and what are my speeds? That is the problem at hand. And if you can do this for one step, and then you can do it for a number of steps. Well, a very natural, natural and maybe also or naive, naive way would be the following. To say, well, the new position is the old position plus the time step times the speed. And since we have both coordinates and speed, we can do the same actually for the speed. So we say the new speed is the old speed plus a time step times the acceleration. And if you just continue this, then you have a new position and you do the whole shebang, you fill everything in the differential equation, bang, you get an acceleration and you crank on the machine, and then you subsequently, in a discrete way, you find the positions and the speed as a function of time. Now, I call this a natural or naive way. Why naive? Well, first of all, why natural? Any ideas why natural? Why do I say natural? Yeah, natural because the derivative is actually defined as q dot at t is defined as the limit of delta t going to 0, where you take qt plus delta t minus qt, and then you divide the whole thing by delta t, right? That is the definition of speed. So maybe I write def here or whatever. Well, if that is the definition of speed, then I can juggle with all these variables, and then I can get what the speed is, because I reorder everything, and then I say qt plus delta t is apparently equal to qt plus delta t times q dot at t, right? Well, almost right. There's one thing which I deleted, which is so here we have an element which is not here, and that is limit. Yeah. So only so this is a limit case definition, and for some magic reason I just drop limit here. Well, not a magic reason, because I have no clue where to put the word limit here or how to do that. I mean, I just delete it. I say, well, it's also for finite things. So in that sense, you could say it's a naive way to do this. Yeah. Or, and you can also look in another sense, it's naive because it's the way you do your calculations in your head. Like, I'm here and I have to be in Amsterdam within an hour. I'm now driving 30 kilometers per hour. Oh, I'm not going to make that. So you're able to make estimates about what your next position is in a finite time. So that's also the naive, maybe. Or maybe smart, I don't know. Anyway, still, where does this thing find its origin? Go back, yeah. Where does this thing finds its origin? You could say in this naive approach, but actually it is in a Taylor expansion of a series expansion of a function. So the Taylor expansion of a function is usually written something like this. F x plus h is the value at x plus h times the derivative plus h squared divided by 2 times the second derivative plus ta 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 ta, and that continues, right? And how does it continue? It is something with h to the power n divided by n. Yeah, I always have trouble pronouncing that in the English language. Factorial, eh? Yeah, because Dutch is so different. And then this is the nth derivative, not the function to the power. Now, looking at this equation, so apparently we did a cutoff here. So any higher order term, so this should read actually plus delta t squared divided by 2 times q double dot plus order delta t to the power 3, right? And actually, we could have done this because we do have the acceleration. So we could have a more accurate scheme for the positions than for the speeds, because we don't have the third derivative. Although, if you just take the equation and you just differentiate it, you have the third derivative. You can do that if you want to. So this is apparently plus order delta t squared. So that is the way where these schemes come from. Okay, now let's go back to our initial problem. An ODE, and that is an ordinary differential equation. Is usually written by mathematicians in the following way. They say y prime is a function of x and y, and then they make an initial value problem out of it, because they say, well, initial value problem, we do know what the initial values are, and we want to know all the other values in time. So the initial value problem is, you say at t is t0, I know that y is y0. You give some initial conditions, and then you say this is the differential equation. Now, why do we say ordinary differential equation? Is it so common? Is it not very elegant? What does the ordinary mean? Or opposed to what? Are there other forms of differential equations? Partial, huh? So this is called ordinary because we only have a derivative with respect to one variable, to time. And if you have differentials with respect to other variables like space and time, you have a partial differential equations because you have partial derivatives. Now, partial differential equations are actually all the differential equations we have, like in fluid mechanics, in finite element method. It's all partial differential equations. If we put time also into, because space is x, y, z, 3 coordinates, and time is the fourth. So at least you have 4 partial derivatives. What we usually do is we find that too difficult. It's like, I cannot solve that analytically. So we discretize, and we are very used at discretizing in space. So we chop everything up in discrete pieces in space, finite element method, discrete blocks, or a grid in a fluid problem. And then we just have bang, a whole number of coordinates variables, but time remains then the variable which is the one you use for differentiating. So then your partial differential equation, by discretization, you brought back to an ordinary differential equation. Moreover, you could also discretize in time and do that. I'm not going to treat that here, but that's also an option. Why not? Okay, back to this one. We have ordinary differential equations. Although we have other things, we have time. So we have something like y dot is a function of t and y. And actually, we don't have that. Actually, we have another form of an equation, right? We have something like m q double dot is q of t and q dot. So we do not have a first order differential equation, but we have a second order differential equation. Now, all the theory in the ordinary differential equation world is all built on this, or on this, which is identical, of course. And we want to use all that theory. So it is sort of handy to bring back our second order differential equation to a first order. And that's actually super simple. So from second order, we go to first order. And how do we do that? By simply saying a new variable. We say p is q dot. We say something like velocity or something like that. And then, so this is already a differential equation, right? And then I substitute all that stuff in here, and then I get m times p dot equals q of t, p, and q. And now I can say, well, I can even collect the p and q in one vector, and I'm going to call that vector y is p and q. And then I can easily write y dot is some function of t and y. Because the first equation is, of course, q dot is p, and the second equation is p dot is minus m times q, which is da 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 da. So instead of having n second order, I now have 2n first order. So that is easy. So from now on, if we talk about ordinary differential equations, I'm only going to talk about these first order differential equations, because you know now how to do that transition. I have an example for a mass spring damper system, but it's so obvious. I'm not going to do that. It's in the book, so if you want to know, read it. The thing which we did up until now, and maybe I have to reformulate, so the following problem, we have y dot is some function of t and y, with some initial values that y at t0 is y0. This is our problem. This is what we want to solve. Now, the naive way we saw, naive way in initial was something like this: yn plus 1 equals yn plus h, and I must define what h is. H is a time step, some delta t. Do I use h every? Yeah. Times the function, the derivative, and the derivative is the function at tn and yn. So this is what we did. This was our scheme of yn plus 1 is yn plus delta t times the speed. Okay, we call this a Euler step. And apparently because Euler thought of that, was the first who invented it, not really I guess, but he was the first who needed to do it. He was the first who needed to do numerical integration apparently. Now we've seen there is some round-off error, some truncation error, so we say this is plus something order h squared, right? So there is some accuracy. And if you get the results after a number of steps and you think, oh, it's not so accurate, what do you do? Yeah.
Time step?
Smaller time step, yeah. And then you get more accurate result, right? Of course, you have to do also more calculations, but that's obvious. And more accurate, more calculations. But there is also another way to get a more accurate result, and that is to use a more refined method. Now, so do you want more accuracy? Two ways, of course. Accuracy. You can make h smaller, smaller. Go back. Or a higher order method, as we say. Now, what is a higher order method? What do I mean by that? Well, there was a mathematician, he was called Heun, and around 1895 he came up with the following plan. 1895. He said, well, the first step I'm going to do is I'm going to just use this this Euler step. So I take this approximation, what do I write? Yeah, function value tn, yn. But I put an asterisk there because it's an approximation. And then in the next step what I do, I say, well, yn plus 1 is yn plus h over 2. And now I'm going to take the average of the derivative at the beginning. Well, we already know that one, we have calculated that one, plus the derivative at the end. And I can do that because I have an estimate. I know at tn plus h, I have my y star n plus 1. So I make an estimate for the endpoint, and then, well, I can make a picture of this. Let's make a picture. So what we do, we have here t, we have tn, we have this initial value yn, and then of course we have a derivative here. Well, let's say this is the derivative, this is this guy. And then we approximate at this moment in time tn plus 1, we approximate a value here which we call y star. It is the value which you would find with an Euler step, but we're not going to use that. We're going to calculate a derivative, and that's probably a little bit different than the initial derivative. So this is this guy. Because there's curvature in your solution, and due to it, the curvature means change in derivative. And then I take the average of this one and this one. I cannot draw that, but then I take the average and then I add that up. So I will not get here because this one is a little bit smaller. So I will end up probably here. And of course I have no clue what the intermediate thing is, so I just do dots, but this is something like that. So this is then the approximation. Now why is it better? Well, if you look at the formula, it turns out that the error you make here is plus order h to the power 3. So the truncation error you make. Meaning that you're more accurate within this one step. Of course, you also have to do more work, twice the amount of work. Okay. So let's summarize. For Euler, we have in one step we have an error epsilon which is of the order h squared, and for Heun in one step we have an error which is in the order of h to the power 3. Now actually I'm not so interested in these local truncation error. I'm more interested in the error which we have after a finite interval. Because you get the task to integrate your system and you say, well, after 1 hour, what are the results? So you want to have a final time. So you want to know the results at t is some capital T, at some final endpoint. And if you have to refine your step, you have to do more steps. In other words, so the more you refine your step size, the more you have to calculate, the more local errors you make. Oh, that could go wrong, right? Because then you think you're getting more accurate, but you're not. So how many steps do you have to make? So the number of steps is apparently the total time divided by the step size, h, right? So the global error being the error at t, is then equal to t over h times this local error, this epsilon. So meaning that of course the order goes down with 1. So for the global error, which we call capital E, that's how we define it. So for Euler, apparently the global error, capital E, is of the order h, and apparently for Heun, the global error is then of the order h squared. So that's nice. Heun is an accurate system. It has quadratic convergence. If you make your step size smaller, linear convergence is always horror. That's so much work. It's a little bit compared to finding zeros. Then with the Gauss-Newton process, that's a second order process that converges very quickly. And the same here. Okay, so that about all our convergence. And now the order just tells us how the error behaves. Actually what we want to do is we want to have a calculation, and then we want to know how accurate is our result. So in practice we want to estimate our global error. So in practice, we estimate the global error. And how do we estimate the global error? Well, if I would have an idea, then I would just calculate with a step size, and I would take half the step size and do it again, and then look at the results. So a naive way, again, would be you take a step size, for instance this one, and then you get the result. Y at my end time is 3.14289. Yeah? They say, oh, let's do it again. We do it with h is 0.05. Oops. So we refine it, we halve the step size. Then I calculate again, and then what I get at my end time, I get 3.14129. Now, what do you think is the accuracy of the results? How many digits? 2? Well, Yeah, digits is all the numbers, also before the digit. Yeah, yeah. That I would say too. I mean, those are identical. The 3, the 1, and the 4, and the rest. Oh, I don't know. So yeah, it looks in a naive way. You would say, well, my true answer is probably something like this, 3.14. So I have only 2 significant digits after the comma. It's not a comma, it's a dot here. But anyway. Well, actually, there is even a basis for that, because you know that your result, the result you calculate, y, is the true result, so the true answer, which you don't know, plus some error. And the error behaves like some constant h to the power p. And p is the method, right? So if we had p is 1, then we were doing Euler. And if p equals 2, then we were doing Heun. Yeah? So if you know this is my result, and this plus should actually be plus or minus, because of errors can go up or can up and down, then what are we actually doing? Well, we have 2 calculations. We have the one calculation is with h, step size h, so we have the result at h, yes, with step size h is some true answer plus c1 h to the power p, and the other one is h over 2. I have divided as an example, I've divided my step size by 2. And then we get c1 h over 2 to the power p. Now we have 2, and actually this should be plus and minus. We have 2 equations, and we also have 2 unknowns, right? Because we don't know what C1 is, and we don't know what the true answer is. Now, formally, with the plus and minus, it's not 2 linear equations. So if they were really linear equations, then 2 equations, 2 unknown, you were able to solve one unique solution. So here we have to fiddle a little bit with a plus and a minus, but still you can solve, and you can say, well, apparently the error estimate, the error I make, the C1, is as such that the true answer minus the result from h over 2, so this result, the last result, the error in that can be estimated from these 2 by this 2 to the power p, the 2 comes of course from this one, 2, times the absolute value of yh minus yh over 2. If you solve that. So apparently we did a pretty good job by saying, oh, let's look at the difference between 2 step sizes, and that should be the answer. Now apparently there is some constant in front of it, and of course the constant for the Euler method is 2 to the power 1 is 2 minus 1 is 1. So for Euler we were really in business. For Heun 2 times 2 is 4, minus 1 is 3, 1 over 3. So it's a mild constant. It doesn't change so much. I mean, the method is approximately anyway. But it gives you a nice way to make an estimate about the accuracy of the result. Coffee. I need coffee. Let's do coffee break. Yeah.
One quick question.
Let me stop the recording and stop the streaming.